Alrighty, I guess we'll get started here. So my name is Cody Osterman. I'm the technical director at Pure Storage for VMware Solutions. What we're going to be talking about today is really queuing inside of ESX and how it works. Right? The different parts of the ESX storage stack, mainly focusing on generally block storage, right? So iSCSI, fiber channel, whatever, and going the ins and outs. This really actually started, my investigation in a lot of this stuff was about 6-7 months ago, when I got a lot of questions about, hey, what should I set my queue depth limits to? Is there a recommended value? And there was a lot of different recommendations across different vendors. And I just wanted to just give a number. I wanted to understand why, and I think that's really the kind of the whole goal behind this discussion. So let's get into it here. First, let's understand the issue. You know, kind of what queuing is and what that really means from a storage perspective. The different queues inside of ESX, and then of course a walkthrough of a troubleshooting situation, one that I commonly see customers go through. Right? If I have this problem, where do I look to solve it, and how do I actually solve it? And then we'll talk about a couple of vSphere performance management tools and also some array-based tools that can allow you to control this in a more dynamic fashion and how those work. So let's get into it. So first off, what is a queue depth limit? Right? So a queue is essentially a line. Right? Using the example of like a grocery store. Right? If I have one register, one clerk at that register, I can handle one customer at a time. My queue depth limit is 1. Anyone after that has to wait. Right? If I have 2 registers, my queue depth limit is 2. I can handle 2 customers at a time. Right? Anyone after those, they have to wait, right? Inducing latency, right, at their time at my grocery store or whatever. And this is, from a storage perspective, it's really no different. The amount of IOs you can handle at once, sometimes they're called outstanding IOs, sometimes concurrent threads or in-flight IOs. Essentially, though, when you boil it down, it's how many IOs some part of the stack is willing to let go down further. Right? If you have a limit at the device, this is how many you can send to me and I'll process before you have to wait to send any more. So there are a couple different queues. Right? There's going to be often a storage array depth queue depth limit. Right? And this could be on a target, on your, a port on your array. This could be on an individual volume. Right? Different arrays have different management around that. There's also a device queue depth limit. Right? On the actual device presented via FC or iSCSI to your ESX environment, there is a limit set in the HBA for how many outstanding IOs it can handle, or it is willing to pass forward or further down the stack. There's also a virtual SCSI queue depth limit inside of the virtual machine itself. And there's also a limit per virtual disk inside of that virtual SCSI adapter. All right, and so these are the 4 main places that you can run into queuing in the ESX storage environment. Now there are things like in the SAN, like buffer credits and so forth. I'm not really going to get into that today because that's generally not the most common issue. It's usually involved in one of these 4 spots. And by the way, I will post this PowerPoint on my blog, so if anyone actually wants it, they can download it. Right? I'm happy to share it. So this is an important thing to note. Right? ESX is designed by default for fairness. Right? Just architecturally, it is a shared architecture. Right? And it knows there's going to be multiple virtual machines, multiple virtual disks, multiple data stores vying for resources. Right? Whether it's, CPU, whether it's memory, whether it's IOPS, right? Throughput. And so by default, ESX lowers some of these limits, right? So nobody can go nuts and hurt someone else by default. Many of you have probably experienced this. You have a physical server, a SQL server or whatever, and it's doing 150,000 IOPS or whatever. And then you convert it to a virtual machine, either by manually recreating it or VM converter or whatever. Same CPU, same memory, maybe even the same volume, literally, right? You just repurposed it and put it on VMFS. But it's getting a third of that performance, a fourth of that performance, right? It's because VMware is throttling things back by default. Like, they don't want anyone to take everything over. So let's go into a little bit of details on this. So the first thing you want to consider is your array, right? This is the lowest part of the stack when it comes to the storage environment. Do you have a queue depth limit on your volume, on your target? If you do, the answer to this often, if you need to push a lot more performance, is parallelization. adding more volumes, adding more front-end ports or whatever. Right, this is one of the reasons older VDI reference architectures included 40 volumes. Not because you needed the capacity, but because often maybe you needed the spindles for one situation, or just literally you were limited by queue depth. And the VDI environment wasn't pushing all this workload all the time. It was just to survive that boot storm, right? Because you'd run out, you'd exhaust that limit, right? So if you have some kind of limit on the array, this is the first thing you want to look at. Because if you have this limit, anything above it doesn't really matter that much until you can actually get the lowest level to offer the performance level you're needing, crossing all the resources that are using it. So let's move into ESXi. So what are the different parts of ESXi and the storage queues? Well, the first thing is the HBA device queue depth limit. And this is how many outstanding IOs you can send to a given physical device on that HBA before they have to wait inside of ESX. All right, hey, I'll pass 64 down at a time, but after that, you've got 65 needs to wait. And 65 is going to get latency, right? Because it's sitting there waiting, doing nothing, waiting for a slot to open up in that queue. And depending on your vendor, right, these default settings are slightly different, or the methodology you're using, or protocol rather. Right, QLogic 64, that changed, I think, in ESX6 or something like that. The rest of them are 32. Software iSCSI is a little higher by default. It's 128. Right? And these are the default limits the HBA will allow for those each individual device presented through it. And these are often, to change these, most of these require a host reboot. Right? So if you want to change this from 64 to 128 or to 32 or whatever, you need to reboot the host to have that come into effect. And so this part is usually well understood. And it's also well documented by most of the vendors. The next part is where it kind of gets confusing. This is where there's a lot of kind of different descriptions on blogs and things like that. And it's a setting used to be called Disk.Sched NumReqOutstanding, DSNRO. The reason I say formally is that prior to ESX 5.5, it was a host-wide setting, and that was the name of the setting. It is no longer a host-wide setting. It's a per-device setting, and it has a slightly different name. DSNRO is just what everyone still calls it. So I'll be using that probably for the rest of the presentation. What it's officially called now is number of outstanding IOs with competing worlds. And you can see this configuration when you do a listing of that device inside of ESXCLI. This will show what that HBA is currently reporting back up to the VMware layer as its queue depth limit. In this case, it's 128 for this given device. So this is also a recent change. DSNRO, or number of outstanding IOs with competing worlds, you can see there's a reason I'm saying DSNRO, a little easier to quickly say, is defaults to 32. That's the first thing, right? DSNRO defaults to 32 for all your devices. It can be changed, though, and this is an online change, right? You don't have to reboot the host or unmount the volume or anything like that. It's an online change. And it can be set in 6.0 and earlier to a maximum of 256. But in 6.5, this has changed. It now can be set to a maximum of whatever the HBA device queue depth limit is. Right? So this could be higher, this could be lower than 256. If the HBA queue depth limit is 32, well, that's the max you can set DSNRO to in 6.5 and later. And so the two questions you might ask is, why did they make that change? And why does this even exist? Well, first off, DSNRO is a hypervisor level queue depth limit. Right? It's a one kind of overriding setting for the HBA device queue depth limit. If you only have one VM or 0 VMs on a given device, DSNRO is ignored. If you have more than one VM on that host, on that device, then DSNRO is calculated. This is to provide additional fairness, once again, in multi-VM environments. The single VM is like, well, whatever, just keep it open to whatever the HBA supports. So what is the actual effective queue depth limit with these two values? Because they're essentially the same values. This is a hypervisor level queue depth limit for this device, and the HBA is an HBA level one. So what is the actual number when these two come into play? The effective queue depth limit is the minimum of these two. Right, so whichever is lower, that's what it's going to be. And this is the reason that VMware made this change in 6.5, is why allow DSNRO to be higher than the HBA queue depth limit. It just causes confusion. Right? If you set it to 512 and you're like, hey, why is this still stuck at 256 or whatnot? Right? And so the minimum of these two values is going to be your effective queue depth limit. Now, if you only have one VM then it's going to be your HBA queue depth limit. So let's move a little bit higher into the stack. So, as I mentioned before, there are two queue depth limits inside of your virtual machine. And that's an important thing to note, is that it's inside of your virtual machine. ESX is not aware of these limits. It is not aware of when these limits are surpassed. So if you surpass these limits inside of a VM, either the per virtual disk or the per virtual SCSI adapter, and you're getting latency, ESX thinks everything's beautiful. Right? You might have an end user saying, hey, my latency's super high. Like I'm seeing spikes of 20, 30, 100 milliseconds. And you look at ESX and say, hey, this is all sub-millisecond, looks great. Probably means you've exceeded the queue inside of that VM, and ESX has no idea. Right? The layer below does not know about queuing the layer above. If it's bad in the VM but fine in ESX, ESX doesn't know about it, neither does the underlying array. Right? If it's bad in the VM, bad in ESX, but fine on the storage layer doesn't know that, right? That latency is being introduced higher above it. And I'll walk through that process during the walkthrough. So anyways, if you look in ESXTOP, you will not see this. And changing these queue depth limits is something that you do inside the guest too. Right? You can configure these limits, but this is something not done in ESX tools. It's literally inside the VM. So Windows registry change or Linux, there's some config files you can use. So what are these numbers and what are the recommendations around this? So I'm going to focus this on Paravirtual SCSI. By and large, I think actually unanimously, all vendors and VMware recommend for best performance the Paravirtual SCSI adapter. It usually defaults to LSI logic, right? And that's fine for most workloads, but for high performance workloads, this is recommended. And this is recommended for two reasons. One, at high IOP, high throughput workloads, you're going to see much better CPU efficiency with PVSCSI. Now, if you're doing 150 IOPS or maybe even 1,000, probably not going to see a difference, right? And you're perfectly fine probably using LSI logic then too, right? So you're building out VDI environments that are doing 30 IOPS, no need to do this, right? But if you're pushing high performance workloads, there's a benefit from a CPU perspective. Furthermore, the traditional LSI adapters have lower possible queue depth limits, default and maximum. Paravirtual SCSI is much higher. The default for Paravirtual SCSI for a virtual disk is 64. And the overall for that virtual SCSI adapter is 256. And both of those numbers can be quadrupled. All right, so if you need to push a lot of throughput, a lot of IOPS to a VMDK, Paravirtual is the best way to go, and you might need to tweak that even higher if you're pushing a heavy workload. Right, and so these can be changed. Now, if I change this, is this going to help me? Well, simply switching to Paravirtual SCSI is not necessarily going to give you better performance. Because remember, there are multiple queues. All you're really doing is just opening the pipe wider inside of the VM. But if that pipe is still narrow inside of ESX, it's just going to wait in ESX instead of inside of the guest. All right, so when a vendor says, hey, yeah, Paravirtual SCSI best performance, that's true, but you can't just change to that, right? Remember, the limit of a VMFS is defaults to 32 outstanding IOs. All right, so just moving to this and getting 64, yeah, you can push more out of that VM, but it's just going to wait at that data store unless you make a change on that level too. All right, so that's an important thing to remember. So let's take a look at some of the performance metrics so we start understanding, all right, these are all numbers and these limits, they sound great, but what does that actually mean for my environment? What does 32 mean? Should I change it to 64? What does that mean? Well, one of the ways to find out if you're exceeding your queue depth limits is one that you're probably all familiar with, is my latency, right? Do I have bad latency? And so there are different latency metrics. It's important to understand what they are and where they are in the stack and how they're calculated. So the first latency is application latency. This is what your application actually sees. Right? The application running inside of the VM, from the time that I/O gets through the VM guest OS stack, through the virtual SCSI adapter, through the ESX kernel, down through the SAN, down to the array and back, right? Read or write. Right? That is what the end user is experiencing. Once again, VMware has no idea if this is good or bad. It only knows about itself and what's below it. Then there's what they call the GAV, guest average. This is the latency as seen by ESX once the I/O has been sent into the VM. Hey, this is how long it took ESX so once it got that I/O to send it the whole way back and send it back into the VM. Right, so if an I/O is waiting in the VM, because of queuing from the virtual SCSI adapter or something like that, GAV is not going to know about it, right? GAV is reported inside of ESXTOP, and it's only going to know about latency that's reported inside of ESX or on the array, right? So if it's queuing, the only time you're going to see that latency, if it's queuing in the VM rather, only latency that's going to report it is the application, not GAV. Then there's the kernel average. This is how much time an I/O is actually spending inside of the ESXi kernel. If this is anything but 0, you have some level of queuing. It's possible resource contention, like your CPUs are maxed out or memory or something like that. That's usually pretty easy to tell if that's the case on a host. If that's not the case, if that's non-zero, you are queuing and those I/Os are waiting inside of ESX. Then there's the disk average. Right? This is the last or the lowest latency that VMware, or ESX in other words, is aware of. Once it's gone through the ESX kernel stack and all that stuff, how long does it take for me to send it out of ESX, out of the HBA, through the SAN, back to the array, have the array do its thing, and return it back to me? Then there's, of course, the SAN latency. How long does it take to get through the SAN? Right? And there are multiple round trips for a given I/O through the SAN, and I'll talk about what that means in a second. And then finally, there's the array latency. Right? How long does it take for your array to process the data? And this can vary how this is calculated from vendor to vendor. So let's talk a little bit about what that means. So let's look at a write, how an array might report a write, and how that might be different from a latency that disk average shows. So first thing that happens is ESX submits the write request to the array. This is when the disk average latency timer starts. There's one trip across the SAN. The array does not know about that time. Right? It's just sitting there waiting. It hasn't received anything yet, so it does not know how long that write request took to get there. Then the array gets that write request and allocates a buffer and sends back to the host, okay, I'm ready for the actual data. There's another trip across the SAN. That is when sometimes arrays start reporting latency. Most do not, though. Sometimes it does. So once again, certainly talk to your vendor if you have questions about how they report their latency. Now, the host sends the actual data to the buffer. So that's another one-way trip across the SAN. This is often where the actual array starts their latency timer. Right? How long does it take me to actually get the data and process it and commit it or whatever, and then return back the acknowledgement? Once that acknowledgement is returned from the array, meaning it's committed that data to whatever, it's cache, it's disk, it's NVRAM, whatever it happens to be, the array latency stops. Sends back the acknowledgement to ESX. ESX gets that acknowledgement, and then its timer starts. So what you can tell from here is that disk average is going to be slightly higher than what your array reports, right? Because there are two one-way trips, one round trip, of the SAN that's included in disk average that the array does not have. So they're going to be slightly different. And of course, there's always averaging around it, so once again, how your array averages your volume latencies and things like that can change. But conceptually, this is how it works. So what about read latency? Reads are slightly different than writes. So in this situation, ESX submits the read request to the array. Disk average starts. One-way trip across the SAN, the array receives that request. It doesn't have to send an acknowledgement back. It's like, oh, you want this data? Okay, great. So the array latency starts. It gets the data, populates it, sends it back. Right? And so the array latency is beginning and end right there, right? Pretty quick. Then there's one more trip across the SAN. The host receives the data, it stops. So the point here is there are some differences between disk average, right, and the underlying array average for latency between reads and writes. So you'll see a slight difference. If there's a large difference between these two, we probably have something going on in the SAN. If it's really more than like 0.1 milliseconds or something like that, you have some problem in the SAN. So we see our latency is bad. Okay, great. Latency is bad. Why is it bad? Where is it bad? What's causing it to be bad? And this is very often can be queuing. So how do I tell if I have filled my queue depth limit? Well, there's, first off, what is my queue depth limit, right? I mean, we could calculate it and all that kind of stuff. But is it reported somewhere? Well, of course it is, right? So there's a number or a metric called DQLEN that you can see inside of ESXTOP, you know, SSH and ESX, and hit, you know, ESXTOP and then U, and you'll see DQLEN. This says what the effective queue depth limit is for that given volume. Right? And many of you probably have looked at this and seen it bounce around. What that means is that you have VMs that are going inactive and active, and occasionally you drop from 2 to 1. And then, oh, I don't need DSNRO anymore, I'll look at the HBA queue depth limit. Right? This is one of the reasons you want to have those values probably the same, so it doesn't bounce depending on how many VMs you have on that data store. So this will dictate what the actual limit is. There's another metric called ACTV, active. This is how many outstanding IOs are currently going against that device. This will never exceed DQLEN, right? Because this DQLEN says how many active IOs can be there, and active says how many are actually active. If there are more than DQLEN, they go into queued. Queued is how many IOs are waiting for a slot to open up in DQLEN. If queued is non-zero, latency is adding, right? Because these IOs are waiting inside of ESX kernel, right? If queued is non-zero, or KAV says how long they're waiting in that queue, you've got queuing. Right? So if you see a high QAV or anything but 0, and then you go look at queued and it's not 0, then it's definitely queuing that's causing that problem. So let's actually walk through an example to make some sense out of this. Right? And there is actually some math around calculating your IOPS based on latency that we can use to say, do you actually need to change this number for your array? And we'll talk about that. So let's walk through a quick issue here. I have a workload. In this case, I was using VD Bench to just, hey, push as much IOPS as you possibly can using 96 outstanding IOs. So I want you to be sending 96 IOs before waiting for acknowledgement to send more, right, to a single virtual disk. And I am using Paravirtual SCSI in this instance. So first question is, can my IOPS even be calculated? Do I know I have a problem? And the answer to that is yes. So there's a law out there, it's a very simple thing, called Little's Law. It says if something takes so long, in this amount of time, you can do it so many times, right? If it takes me 1 minute to pick up a rock, and I'm given an hour, I can pick up 60 rocks, right? If I can pick up 2 rocks at a time, I can do 120 rocks in an hour. And that's basically what Little's Law says. If it takes you so long to do something in this amount of time, this is how many times you can do it. This is how you can calculate IOPS, right, if you know your average latency, the average time it takes to process it. And you can get pretty close to figuring out what that IOPS is going to be if you know the amount of outstanding IOs you're pushing. All right, so let's use our grocery store analogy again. Right, if a customer takes 1 minute to get through that line, you can serve 60 customers an hour, the IOPS. Right? If you double that outstanding IOs, right, you can do 2 at a time, you can do 120 customers an hour. So let's do some quick math based on our workload. In 1 second, there's 1,000 milliseconds. If my average latency on my array for my IOs is ½ a millisecond, that means with 1 outstanding IO, meaning I send 1, wait for it to finish, and send another, I can do 2,000 IOPS. If I'm doing 96 outstanding IOs, meaning I'm sending 96 before waiting for any of them to be acknowledged before I send more, I can do 192,000 IOPS at that average latency, right, with that workload. So what that would expect is that I should be pushing 192,000 IOPS. Well, as you can probably guess, I'm not. And what this VD Bench readout shows, you may not be able to read it in the back, but it says I'm doing 65,000 IOPS, give or take a few, and my latency is about 1.4 milliseconds. My array latency is reporting at 0.4 milliseconds. So what's the problem here, right? Why am I not getting 192,000 IOPS, and why is my latency so high? Well, let's go through these settings and metrics. So, ESXTOP. So my Paravirtual limit is 64 per VMDK, right? So the VM can send out 64 at a time. And if we look at ESXTOP, we see a couple things. We see DQLEN is at 32. That's the default. We have 32 that are active, meaning 32 are actually making it through. And then we see 29, which it's a sampling error, it's basically 32, that are waiting. So the first thing is, why am I not, I mean, okay, I understand why I'm only doing 32 at a time, because that's my limit on my data store, but why am I not seeing 64 waiting? Well, because the guest can only send out 64 at a time. Yes, my workload's doing 96, but 32 of them are waiting in the VM, and it can only send out 64. And And then when we get down to the data store is like, hey, I see you're sending me 64, but I can only handle 32. And so 32 more are waiting inside of ESX. Right? So I have 32 IOs waiting inside of my VM, and I have 32 IOs waiting at any given time inside of ESX, both adding latency. And because my overall average latency is much higher, I can do less IOPS, because everyone's waiting, and we're waiting in two parts of that stack. So let's fix it. First thing we want to do is like, well, I want to be able to get all 96 IOs at a time out of my VM. So I can go into my virtual machine. In this case, I'll do the example of Windows. It's a registry change, right, for Paravirtual. To change it from 64 to 96 or 256 or whatever you want to do. So I change that and I restart my workload. Nothing happens. I'm still doing about 65,000 IOPS. I'm still getting 1.47 millisecond latency. Why is that? Well, you can probably guess, right? We still didn't open up the VMFS layer, right? There's still IOs waiting down there at that data store. And if we look at ESXTOP, before we made this change, we see my disk average is about half a millisecond. If you remember, my array average is about 0.4. And that 0.1 millisecond difference is what we talked about earlier with the reporting difference between the array and disk average. Kernel average, we see 0.4 milliseconds, meaning that before we made that Paravirtual change, the IOs were waiting for 0.4 milliseconds inside of ESX. So the overall latency as ESX saw it was about 0.9, not 1.4. So that additional latency was due to the queuing in the VM. Now, if you make that change to allow all those IOs to make it out of the VM at once, all that happens is instead of queuing in the VM, they're now queuing down inside of the ESX kernel. Right? And so now ESX sees the true latency, if you will, of the guest, because all the queuing is occurring inside of it. So we didn't really improve performance. We just gave the VMware administrator some insight into what's actually going on by opening up that VMDK queue. So do we want to move this bottleneck? Should we change it? Well, maybe you do, maybe you don't. Right? Maybe I don't necessarily want, I want my VM to be able to pass everything out of it, but I want ESX to control the fairness. Right? I want my VMs to be maxed, and I want ESX to control the fairness and hold some VMs back or hold certain data stores back. So maybe you'd stop here. But if you want to solve the performance problem, we need to push forward. So once again, let's fix it. So I'm going to change my HPA QDEP settings in DSNRO to 96. So now my DQLEN is listed at 96. So let's restart the workload. Now my latency in the guest, my VD bench printout here, is 0.7 milliseconds. And my overall IOPS is 137,000. Right? So by simply changing my QDEP limit in the VM and ESX, I doubled the amount of IOPS I'm doing without reconfiguring my workload or really changing anything from the application standpoint, just allowing it to do more at once and not have to wait for the other IOs that it sends. So great, higher IOPS, higher latency, or lower latency. But let's look at those numbers again. So my overall latency is 0.7 milliseconds. And doing all that same math again, right? We calculate that at that latency, our expected IOPS to be 137,000. That's exactly what we had, right? It's great, math works. But the question you might have is, why am I not getting my 192,000 IOPS at this point? I've opened up the queue inside of my VM. I've opened up the queue inside of ESX. It can push everything that it wants to push down. Why am I still having higher latency? Why is it 0.7 instead of 0.5 as what ESX reports? Well, at this point, you know there's contention in that virtual machine. Right? There's nothing queuing in ESX. The array looks fine. The SAN's fine because the disk average is low. So something in the VM is causing a problem. In my case, I was using VD Bench. When you push a lot of workload, you have to actually use multiple Java virtual machines, and by default, it uses one. And so I actually had resource contention from within VD Bench to push this workload, adding about 0.2 milliseconds latency and decreasing the amount of IOPS that it could push. Right? So a lot of knowing this is not necessarily having to change it, but a little bit of a path to innocence. Yes, it's the storage. Yes, it's ESX. Yes, it's the VM. Yes, it's the SAN. So in the end, so back to these values. Does it matter? Should I change it? Should I change my QDEP limits? So it kind of depends. right? And so this, I go back to all flash arrays here because this is where the question comes up a lot more than it used to. If I have an AFA, should I change it? And then we'll talk about if you don't have an AFA too. I differ from a lot of recommendations out there, at least my best practice for Pure, and I say I don't think you really need to, right, with AFAs. A lot of them out there say you do, and that's perfectly fine. Always follow your vendor's best practices, but let's kind of look about the math around this. Going back to Little's Law. One thing about AFAs is they have very low latency, right, sub-millisecond. We all talk about that, right? Pure, SolidFire, EMC, HP, we all talk about having low latency on AFAs. And they can take a lot of concurrency, right? It's flash. So, do we need to change these default values? At a default queue depth limit of 32, with an average latency of 0.5 milliseconds, that means you can push 64,000 IOPS per data store per host. You add another host to that, you can now do 128,000 IOPS to that data store. How many in here are pushing more than 64,000 IOPS per host per data store? Yeah, I saw maybe one hand, I don't know. Right? So this is kind of the reason that I say I don't think you really, if you have an AFA, you don't really need to change this value because I'm kind of like, hey, it's not broken, don't try to fix it. And anytime you make a change in ESX, if you open a support case with VMware or whoever, and they look at this, why is this changed, you have to then explain it. All right, so keeping with defaults is usually a good practice unless you need to make a change. VMware does things for a reason. Right? So, when should I change it? Well, if I expect to do more performance than that. Right? I'm going to be pushing, I'm pushing 200,000 IOPS to this VMDK. Yeah, you're going to have to change it. Right? Yes, also maybe if my latency is much higher, right? If I'm using a spinning disk array or something like that, which has higher latency, every slot in that queue is then worth less, right? Because every I/O takes longer to process. It empties out that queue slower, and therefore you can do less IOPS, right? So if you need to push a lot of IOPS and you have a high latency array, then you might want to look at upping this. But there's a downside, right? If you push a lot of concurrency to an array that has high latency, that latency is probably going to go up and up and up until it gets really bad, right? So you may not want to do that. So generally no, because most workloads are distributed, right, across data stores or at very least across hosts, right? And every host has its own queue. So you generally don't need to do that. And like I said, if AFAs, because they empty out that queue so fast, that queue is worth so much more. Right? So let's look again about the situation of should I change it if I have high latency or not, or should I change it in general? Like maybe I want everything available, let's go for it. Remember, once again, ESX is designed for fairness by default. What happens when you overwhelm a queue? What does it affect? Well, everything on this planet has a saturation point, right? Every system, every interconnected system has bottlenecks and has saturation points. Once you saturate it, everything very quickly goes downhill, right? When we hit that point, things go bad fast, right? I mean, we drive to work at 7:25 a.m., oh, traffic's okay. 18 more cars get on the highway, everyone slows down, right? Because you hit the throughput limit of that, the IOPS limit of that highway, right? So this is why, highways have on-ramps with traffic lights slowing them down, right? Yes, the people waiting at that traffic light are going to be slowed down, but the people already on the highway get to keep on going on at the speed they are, right? Are affected less. So whenever you open up a queue depth at some layer, is potential for something below that layer to be affected, which you may or may not want. Because you'll run into this, right? So on that note, are there things inside of ESX to help me control this? Are there things inside of the array to help me control this? Maybe I do want to open it all up. And the answer, of course, is yes. But once again, it's important to understand how these things work. So let's talk a little bit about some features inside of ESX. So there's a couple things, right? Adaptive queuing, storage I/O control, storage DRS, and array-based QoS. Right? These are all solutions offered by VMware and, of course, your array provider to help you deal with dynamic performance changes, limits, controls, resources, shares, throttling, etc. So let's talk about the oldest one, which is adaptive queuing. This has been around since, I think, the ESX 3.5 days, right, or something like that. If an ESX receives a queue full or busy from that target, from that array for that volume, ESX will drop the queue depth limit in half for that volume. And therefore allowing basically the array saying, hey, I am just overwhelmed, is what it's saying. You need to slow down now. And that's what ESX does. It slows itself down. All right, these IOs will wait in my queue, not on yours. And this is controlled by two settings. This is not turned on by default. If you enable this, you make queue full sample size non-zero. And that's basically how many queue fulls that ESX gets in a row before it starts throttling, right? If it gets to 1, well, maybe that was a transitory thing. If it gets 5, then okay, there's a problem. And you can control that by making it something other than the default, which is 0. Queue full threshold is how many good responses it then gets until it starts upping it. And it then, once it gets so many good responses, it slowly increases that queue depth back to the original limit that was specified by your settings and whatnot. So this is one option, right? You could open everything up and then have queue full control it. But that one thing does is that, first off, it requires the array to support queue full busy or queue full or busy, which some do, some don't. So once again, talk to your vendor. They'll probably have best practices around that. And also, once it means, again, for this to kick in, your array needs to be busy, right? Do you necessarily want that to happen? Maybe, maybe you don't. What about other things to stop that from even getting to that point? So let's talk about storage I/O control. So you could, I mean, there's many sessions in the past about storage I/O control. We could talk for probably hours about how this works. But at a high level, right, what storage I/O control does is that you can set shares and resource limits and things like that on VMs in a data store. And if that data store gets overwhelmed, ESX will throttle your VMs according to their shares. They'll kind of throttle how much that each of those VMs can do according to the shares you've given to them on that data store. So the minimum latency for it to see that this has been overwhelmed is 5 milliseconds. So is that a latency that you run into on your particular array? With an AFA, probably not. With a spinning disk array, probably. So it may or may not be helpful. But first off, what latency is it even looking at, right? We talked about 8 or 9 different latencies earlier. What is it actually looking at when it makes these decisions to throttle? So storage I/O control looks at the SAN and array latency. In other words, the DAV, meaning that if there's queuing in ESX, storage I/O control does not respond to it. It is only going to respond to when it sees that actual device on that array is overwhelmed, not just because there's some low setting inside of ESX. So a sustained 5 millisecond latency on an AFA, probably not going to run into it. You've probably run into a pretty large problem. But maybe on another type of array that's useful. Right? So this is something you might want to think about. It may or may not help you. Storage DRS, instead of throttling a VM or two, will move VMs around. Right? If it hits a certain threshold over a large portion of the day, it will move VMs from one data store to another. Right? And the minimum for this is also 5 milliseconds. But storage DRS looks at a different value than storage I/O control does. Storage DRS looks at a value called VM observed latency, which essentially is the array latency, the SAN latency, and the ESX latency, including queuing, aka the guessed average, the GAV. So if you have latency based on queuing, storage DRS can move a VM to another one that might be better off, better data store. So storage DRS can be helpful in situations to control queuing for you. Yeah, I don't want to raise the queue value on this, but I have another one here and it can service more. That might be what you want. Right? And storage DRS and storage I/O control are based on the same kind of 4K random read injector. Right? So what storage I/O control does to kind of dictate performance and see what's going on and decide should I move this VM to this data store or not, is they have a performance operation that runs every so often that does 4K random reads to that device and increasing numbers of outstanding IOs. It tries to figure out, hey, what can this data store do? It even does cool things like it'll run it on one data store in a data store cluster, get the performance, run it on another one, and then run it at the same time. If they see the performance suffers on both of them when they're at the same time, oh, these share resources under it, moving a VM from here to here probably isn't going to help me. Right? So there's a lot of cool stuff that they do inside of it. But really the key thing to remember is what latencies they enact upon. Storage I/O control looks on SAN and array, storage DRS includes queuing. Right? So once again, these may or may not help you. Now, one thing to note about this though is AFA, if you're queuing on an AFA, remember I was doing 96 outstanding IOs and 64 of them were queuing, and I was still only at 1.46 millisecond latency. So 5 millisecond latency is a colossal amount of queuing. And I would argue you might want to look at something instead of turning on storage DRS in that situation. But it can certainly help you. But that is a colossal, because it's also not just about like, oh, what is my latency right now? It's like the 95 percentile over 24 hours or something like that. I don't remember the exact numbers. But once again, it's important to understand what that is. Now the other option here is, of course, IOPS limits. Inside of vSphere, you can set IOPS limits on virtual disks, right? Yeah, you can do 100 IOPS, you can do 2,000, right? In 6.0 and earlier, this is a per VMDK edit settings kind of thing, or in the API. In 6.5, you can set this as a policy, right? All these VMs under this policy can do 100 IOPS or 1,000 IOPS or whatnot. I've had some customers use this in 6.5 with VDI environments quite effectively. I size my desktops for 25, that's what they get. So the last portion of this here is array-based QoS, right? And that's another option. Maybe I want my array to control it all, right? And this is a perfectly valid scenario. I'll open everything up inside of ESX, let everyone do what they can, and then let the array control it. If you're using VMFS, though, vVols, this is a different story, but with VMFS, array-based QoS does not follow the virtual machine, right? It's on the data store. Right, so that's one thing you want to at least consider, right, when using array-based QoS with VMFS, is that it doesn't necessarily follow the VM. Right, so if you move a VM to another data store that doesn't have that QoS, that has a different level, someone storage emotions it, you might get something unexpected, right? So that's something to consider. Virtual volumes, if you're using storage-based policy management to control something like array-based QoS on a VM, that does follow the VM, which makes a pretty nice use case. So, last thing I want to quickly talk about is then, of course, that begs the question, what about virtual volumes? Does queuing inside of ESX change when you're leveraging virtual volumes? How does this work? Is everything I just told you, is it completely irrelevant? Not really. So the first thing to understand here, right, is that with virtual volumes, when you create a VM, every virtual disk you create creates a volume on the array. Right? And the mechanics of how that's done and stuff like that differs a little bit from array to array, but that's always what happens. Every virtual disk you create creates a volume on that array. How those volumes are physically connected back to ESX is through what they call a protocol endpoint. It's one physical device that you create and connect in the normal way, right? Through fiber channelized SCSI, you connect it to your host group or initiator group or whatever your array calls it. You rescan ESX and you see it. When vVols are created, vCenter goes to the array and say, hey, create this vVol of this size, make it replicated, make it snapshotted every hour, whatever, and then connect it to this ESX host. How it connects it is it looks for that host object on that array, the protocol endpoint that's presented to it, or one of the many protocol endpoints if you have more than one, and it does a sub-LUN connection to that PE. Right, so essentially, all the vVols are connected through that one protocol endpoint, or maybe many protocol endpoints. But the key is that there's a lot of vVols presented through one physical SCSI device. So is that going to be a performance limitation? Do you get rid, since there's no more VMFS, do you get rid of queue depth limits? No. There is still a protocol endpoint queue depth limit. It is still controlled. There's still a certain amount of outstanding IOs and a single ESX host can send to a protocol endpoint, right? Possibly limiting the performance that host can push to its underlying vVols, which could possibly be in the thousands. You can have 16,383 vVols per PE. Right? So that sounds like it could possibly be a bottleneck. So there is a setting in ESX that controls the default protocol endpoint queue depth limit. It's very similar to DSNRO, but it's called PVSCSI, Protocol Endpoint Scheduled Number Requests Outstanding. This controls the default queue depth limit of that protocol endpoint, which starts at 128. You can also configure it individually, or you can change the default, up to 4,096. So if we use Little's law, and we use that half millisecond latency number, or even double it if you want to a millisecond, with half a millisecond, that means per host, per PE, you could push 8,192,000 IOPS per protocol endpoint per host. At that point, you probably need more than one array, not more than one protocol endpoint. Of course, it also matters, does your array have per volume queue depth limits? Does a vVol have a queue depth limit? Does a protocol endpoint have a queue depth limit? And that's, once again, a vendor discussion you want to have, how that works. But from the VMware perspective, they've opened it up wide, right? So you should be able to push a ton of performance per PE. But of course, talk to your vendor about the recommendations on how that needs to be done. But conceptually, it's no different than VMFS. There is a queue depth limit for the virtual disks, which are vVols, under its endpoint object, which instead of a file system and all that craziness that goes with VMFS, it's a protocol endpoint, which is just a physical mount point for those vVols. So, in the end, certainly follow your array vendor recommendations around queue depth limits. If they tell you to set DSNRO to 256, that's probably what you should do. What I wanted to just make sure that was understood is how this all works, what those numbers are, and that you can actually intelligently pick a number for your workload. right? Based using things like Little's Law. If you know your kind of average latency, you can get pretty close to what you should be able to do, what you should be seeing. Right? The point of understanding this stack is, once again, the path to innocence for the storage, for the switch, for VMware, for the VM. Right? So at the very least, if you have a performance problem, you can narrow it down to where it is. You may not know immediately why, but you know where it is if you look at these metrics and these numbers. Right? And remember, changing them at one place does not necessarily give you better performance if you don't change it through the stack. And furthermore, if you change it on one host, you should change it on all those hosts in the cluster. You don't want to vMotion a VM and then get a different performance profile. Right? All these reasons kind of conspire together to make me tell people, like, when the question, who's doing 64,000 apps? Probably don't want to change it, right? Who wants the headache of changing more settings than you need to? At the very least, it's important to understand how this works. So that's my spiel. I ran some blog posts and things like that about queuing and protocol endpoints and stuff like that. I go into a little bit more detail on PEs and how that works. So feel free to reach out or whatever and ask me questions. But yeah, and so if anyone has other questions, the mic's up here. I'll certainly be outside afterwards. But otherwise, I appreciate your time and enjoy the rest of the conference.